So section 3.2, we're looking at solubility equilibrium. So we talked about equilibrium as far as chemical reactions go. So when you start with two reactants, they go towards the products, but in some reactions, if you get too much product, it starts going the opposite way, and you end up with a little bit more of the reactant. And they tend to go back and forth until they finish. And it was compared to a pendulum, and that's a pretty good comparison. So if you start swinging in one way, it's going to go too far, and then it's going to swing back. And maybe not quite as dramatic in chemistry, but it's that same effect. So solubility equilibrium, it says while soluble salts dissociate 100%, insoluble salts dissociate a small amount. So if something soluble would be like sodium chloride or sodium nitrate, you can dissolve all your salt in water and it's going to stay as a salt. But there are other things like chalk. You ever tried to dissolve chalk in water?
Yeah.
You've done that? Yeah. Well, your driveway might also be made out of the same stuff, and it doesn't dissolve in water very well. So if you dissolve or try to dissolve chalk in water, only about 1% of it dissolves, and the rest of it just sits on the bottom as not a precipitate, but just as the solid that fell. The maximum amount of insoluble salt dissociates is called its solubility. It's like its maximum solubility. We typically use molarity, but sometimes it's grams per grams of water. That's a little bit different. The equilibrium constant for the dissolution of insoluble salt is called KSP, the solubility product. All right, so if this is our solid salt, and you've got this written down already too, it becomes a cation and our anion. KSP tells us how much of these are we going to get versus how much of it's going to just stay as a solid. So the KSP, I should write this one down right under this. The KSP, you don't have this on your paper, implies the dissociation equation. So sometimes you'll get data like this. Silver chloride has a KSP equal to something. And so this KSP is implying that AgCl2, which is a solid, becomes Ag plus and 2 Cl minuses. And so that's what it's referring to. Most of the time you won't get this equation. It'll just say this is the salt, this is the KSP. Make sense? So in example 1, it says the molar solubility of silver sulfate at 25 degrees is 2.29 times 10 to the negative second molar. So that's the molar solubility. Find KSP. So the molar solubility. So we're going to have to figure out what's going on here. First off, does anybody know the formula of silver sulfate?
Ag2SO4.
Ag2SO4. Is it on your paper already? It is on the paper.
It's on the paper.
Yeah, it is. So silver's kind of different because it's a transition metal, but it always has the same charge. It's always 1 plus. So we end up with this is our solid compound, and we have Ag plus and SO4 2 minus. It's forward. So you already have the table drawn. We just need to fill it in. And this is what you might call an ICE table. Initial, change, and equilibrium. So initially, we're going to dissolve this. The initial conditions is just pure water. So we have no silver ions, no sulfate ions. This is where our little memory trick comes in handy. This is a solid, so it's just, in general, stay out. So then the change. The change is, you could represent it as X, but in solubility it's usually S. So we are going to increase the concentration by some amount, and it's times 2. 2 is the coefficient. So the concentration of silver is plus 2S, and for sulfate it's just plus S. If we were thinking about this, it's going down by S, but we're mostly ignoring the silver sulfate right now. And so my equilibrium, 0 plus 2S, 0 plus S. This is more or less how a lot of these are going to work to start off with. So write the equilibrium expression for this reaction. What is my equilibrium expression going to be for this reaction? It's going to work the same as the equilibrium expressions we learned about in 3.1. So our products are going to be on top and the reactants would be on bottom. But remember, solids stay out of my equation. So it's just going to be the concentration of silver squared times the concentration of sulfate. So we can actually plug in the numbers that we found. So silver is 2S squared, it's this number, and sulfate is just S. So we've got 4, we've got S squared, S cubed. And now what to do with this? We've been using S this whole time. And S is what we call the molar solubility. So you might write this down somewhere. S is molar solubility, which is this number they gave us up here, 2.29 times 10 to the minus 2 molar. And so I'm going to drop down a line. KSP equals 4S cubed, which is 4 times 2.29 times 10 to the negative second cubed. And so this is how we figure out our solubility product. should come up with 4.8 times 10 to the minus 5. Just nodding in agreement. So, in terms of units, this is a value for K. It's an equilibrium constant. Kc had no units. Kp had no units. This is not going to have units either. It's just a number. And look at this number. It's pretty small. It's a lot less than 1. Excuse me. 0.0000. This is the number. On a scale of 0 to 1, it's pretty close to 0 and not very close to 1. When it's this small, when KSP is little, it's really going to favor the original solid. And so I'll even write it here, favors the solid. Let's leave it at that. What does this reaction mixture look like when 0.010 moles of silver sulfate is in a 1 liter solution? So let's duplicate this. Okay. Get rid of some things. So here's what it looks like. What does the reaction mixture look like when 0.010 moles is dissolved in 1 liter of solution? And we end up with, that's just 0.01 molar. Says since the concentration of AgSO4 is less than S, Ag2SO4. These are our two numbers. This is the concentration that the silver sulfate would be in the solution, and this is the molar solubility, or really what is the maximum amount in terms of concentration that would actually dissolve. It's this one. I just wrote it in standard notation so we can compare them. The molar solubility. So if your concentration is going to be less than the molar solubility, it'll dissolve. If it's greater than that, you're going to have solid leftovers. What does this reaction mixture look like when 0.040 moles of silver sulfate is in a 1.0 solution? So let's look at it again. The only thing that's going to change is here. Concentration of silver sulfate, 0.040 moles per liter. This is our new concentration here. And with this one, since the concentration of silver sulfate is greater than S, then only 2.29 times 10 to the negative second molar will dissolve. This is the maximum amount that it can dissolve. The excess will remain as a solid.
Good stuff.
Just eager to say something, right?